Hi students, today I am explaining the derivation of the limiting case of Poisson distribution to normal distribution. So already you know that from one distribution to another distribution approximation we need to some conditions. So here also we are mentioning some of the conditions. See the proof, normal distribution tends to Poisson distribution under the following conditions. The first condition is P tends to 0, r tends to infinity, and rp equals to lambda, that is finite, that is, so from this relation we can write p equals to, it's a product, take this r to this side, so then it becomes p equals to lambda by r. Already you know the, so you are in the revision of by the geometric distribution, and already you know that the probability mass function of normal distribution is p of x equals to x plus r minus 1 c r minus 1 small p power r q power x. But you know the relation small p equals to, we can write 1 by q, small q equals to p by q, so you are substituting here itself. So in the place of small p you are writing 1 by q whole power r, in the place of q you are writing p by q whole power x. In the next step you know the, you can write in another way also the probability mass function, that is x plus r minus 1 c x. So 1 by q you can write it as q power minus r, so p by q whole power x. So but already we know that small p plus small q equals to 1, but in the negative binomial distribution capital Q minus capital P equals to 1. If you are taking minus P this side, it becomes plus P, so therefore instead of Q we can write 1 plus P. So we are substituting these values. So then x plus r minus 1 cx, in the place of q you can write 1 plus p whole power minus r by using this relation. P as it is, in the place of q just you are substituting 1 plus p whole power x. And applying the second condition, consider the limits as r tends to infinity. Now consider both the sides r tends to infinity, then just you are substituting the r tends to infinity both the sides. In the next step, already you know that the formula for ncx or otherwise ncr formula is n factorial by n minus r factorial into r factorial. So in the place of n we are having x plus r minus 1 factorial by r factorial, means x factorial into x plus r minus 1 minus x. So plus x minus x gets cancelled, so finally you are getting r minus 1 factorial. So so limit r tends to infinity, so directly I am writing from this step, so you have to cancel x plus r minus 1. So we are expressing x plus r minus 1 factorial like this, x plus r minus 1, x plus r minus 2, so on, r plus 1, r minus 1 factor. How you know that, madam? Means you have to cancel the denominator value is r minus 1 factorial. So that's why your expansion is done up to r minus 1 factorial. So after writing this expression you can cancel r minus 1 factorial, r minus 1 factorial gets cancelled. In the next step, limit r tends to infinity x plus r minus 1, x plus r minus 2, so on, r plus 1 into r by x factorial, and the remaining terms as it is. In the next step, limit r tends to infinity, we are dividing. So already in hypergeometric distribution what you are doing, x factorial, so how many times you are doing x terms we are dividing, so that's why here we are writing r power x. So means r power x terms we are applying numerator, so that's why we are applying for denominator also, x plus r minus 1 by r. So for all the terms we are dividing with respect to r. So in the next step, x plus r minus 1, so x by r plus r by r means you'll get r gets cancelled, you'll get 1. So that's why here you are writing 1 plus x minus 1 by r. So similarly for the remaining terms also, 1 plus x minus 2 by r, and so on. R by r cancel, plus 1 by r by r cancel, you are getting 1 into r power x, and the remaining terms you are writing as it is. The next step, 1 by x factorial, it is a constant, take it outside. Here whenever we are applying the limits, so limit r tends to infinity, so for each term we are in the denominator we are having r, so the r tends to infinity means the entire term becomes infinity. So the leftover terms are so what is the leftover, this term becomes infinity, 1 plus infinity infinity. So you are getting 1 1 and the remaining term is 1 plus r power x. So here also power x, so r into p whole power x. So 1 plus p whole power minus r, rp whole power x by 1 plus p. So the entire term becomes with power x. So 1 by x factor will take it outside, limit r tends to infinity, 1 plus lambda by r whole power minus. How you are getting this lambda by r? By using this relation p equals to lambda by r. So so 1 plus lambda by r whole power minus r. So but rp means you can write lambda. So in the place of rp you are writing lambda by 1 plus lambda by r whole power x. So then applying limit r tends to infinity for both the terms separately, then lambda power x. So lambda power, how you are getting lambda power x? Here in the numerator you are having lambda power x. So in the here 1 by x factorial. So that lambda power x, take it outside. So lambda power x by x factorial and 1 plus lambda by r whole power minus r. So this 1 by 1 plus lambda by r, so that is in the inverse. So that we can write it as whole power minus 1. So lambda power x by x factorial, limit r tends to infinity, 1 plus lambda by r whole power minus 1. So r power minus 1 means minus r, limit r tends to infinity, 1 plus lambda by r whole power. Actually this is in the denominator, we are writing in the inverse minus x. So by applying limit x tends to infinity, 1 plus lambda by x whole power x equals to e power minus x. So limit lambda power x by x factorial as it is in the place of first term. In the place of first term we are applying this formula. So you are getting e power in the place of x you are having lambda, that's why you are getting e power minus lambda. This value becomes 1. So finally you are getting e power minus lambda into lambda power x by x factorial, which is the probability mass function of the Poisson distribution.